You know, sometimes the most amazing solutions to our biggest problems come from places you would never, ever expect. Today, we're diving into a story of chemical innovation where scientists found a new, greener way to build some really critical molecules. And their secret ingredient? Well, it might just be in your daily multivitamin.
So this molecule right here, this is the star of our show. It's called a trisubstituted epoxide. Now that little three-membered ring is super reactive, which makes it what chemists call a privileged building block. Think of it like a master Lego piece that can unlock the structure of tons of new medicines. And the more stuff attached to it, the trisubstituted part, the more complex and valuable the drugs we can make. The only catch? They are really, really hard to build.
But here's the crazy thought. What if the key to making this molecule efficiently and in a way that's good for the environment wasn't some rare, super expensive metal, but something you could find in your own kitchen cabinet?
So here's our game plan. We're going to start with why these epoxides are such a big deal. Then we'll meet the vitamin that's powering this whole reaction. We'll see how the scientists figured out the perfect recipe, and then look at the awesome results. We're even going to peek under the hood at the reaction itself before we wrap up with what this all means for the future of chemistry.
All right. First things first, let's really get a handle on the challenge here. Why are chemists so obsessed with building these specific molecules anyway?
Like we said, epoxides are a huge deal. That ring structure is under a ton of strain, which makes it incredibly reactive. Now, that's a bit of a double-edged sword. It makes them fantastic for snapping into place to build bigger, more complex molecules, but it also means they can be kinda unstable. They're like these high-energy puzzle pieces, absolutely essential for the final picture, but they might just fall apart before you can get them in place.
And the most useful epoxides? They're often sterically hindered, which is just a chemist's way of saying they're really crowded. Imagine trying to build with Legos, but all the little connection points are surrounded by other bricks getting in the way. That's the exact hurdle scientists are facing, and it sent them on a major hunt for better, more clever tools.
And that, right there, brings us to the breakthrough. Instead of using the usual heavy hitters like heavy metal catalysts, the researchers behind this work looked for a more elegant and, frankly, much greener solution. For a long time, reactions like this relied on metal catalysts. We're talking about precious metals, things like palladium or rhodium. And look, they work, but they can be toxic, they're super expensive, and they can leave behind nasty impurities. The alternative is something called organocatalysis, which uses small organic molecules, things based on carbon. These are usually way cheaper, much safer, and a whole lot better for the planet. And the organocatalyst at the heart of this story? It starts right here. This is thiamine hydrochloride, but you and I know it better as vitamin B1. Yep, that's right. Researchers realized that this common vitamin could be the starting point for a seriously powerful molecular machine.
With just a little chemical nudge from a base, vitamin B1 morphs into something called an N-Heterocyclic carbene, or NHC for short. And NHCs, well, they're basically superstars in the world of organocatalysis. They are incredibly versatile little tools that can persuade molecules to do all sorts of chemical acrobatics that they would never do on their own.
So they had their star player, this catalyst made from vitamin B1. But getting a chemical reaction to work perfectly, it's a lot like baking. You've got to get the ingredients, the temperature, the timing, everything just right.
This here is a peek into that scientific detective work. You can see the researchers tweaking the recipe, bit by bit. Just look at the base they used. That's what activates the catalyst. A weaker base like DBU only gave them about 15% of the product they wanted. Pretty dismal. But when they swapped it for Et₃N, boom! The yield shot way up. And then the oxidant, the ingredient that actually builds the epoxide ring, most of them gave 0. Absolutely nothing. But one, aqueous TBHP, worked like a charm.
And after all that trial and error, this was the magic number they landed on, 73% yield. Let me tell you, in synthetic chemistry, for a brand new, complex reaction like this, that is a fantastic result. It means the recipe doesn't just work, it works really, really well. And here it is, the final perfected recipe. You've got the vitamin B1 precursor, the base Et₃N to get it going, the oxidant TBHP to do the heavy lifting, all cooked up in a solvent called DMF at 120 degrees Celsius. Every single one of these components is absolutely critical to hitting that awesome 73% yield.
Okay, so a great recipe is one thing, but can it handle a few substitutions? The next big test was to see if this new method was just a one-trick pony or if it was a versatile tool that could make a whole family of different epoxides.
And the answer? A huge yes. The researchers threw a whole bunch of different starting materials called chalcones at it. By tweaking the structure of these starter molecules, adding different chemical groups here and there, they found the reaction delivered time and time again. This meant they could create an entire library of these valuable epoxide compounds, each one with its own unique properties.
This quote from the paper really says it all. Basically, it means the reaction isn't picky at all. It didn't matter if the starting materials had chemical groups that pull electrons away or groups that push them in. The method just worked. And that kind of robustness is exactly what chemists dream of, because it means this reaction can be adapted to build a massive range of new molecules, like potential new medicines.
Okay, so we know the recipe works, and we know it's versatile. But what is actually going on down there at the molecular level? How in the world does vitamin B1 pull off this incredible transformation?
Here it is, the elegant step-by-step molecular dance. First, the base flicks the switch on the vitamin B1, creating our active NHC catalyst. Step 2, the catalyst goes on the attack, hitting the starting material. Now, step 3 is where the real magic happens. It's a tandem reaction, which means it all happens in one seamless sequence. First, the molecule gets emitted. It reacts with the solvent, DMF. Then, immediately after, it's epoxidized when a radical from our oxidant, TBHP, comes in and forms that final ring. It's a beautiful 1-2 punch. And finally, the brand new epoxide is released, and our vitamin B1 catalyst is born again, ready to start the whole cycle over. It's just a wonderfully efficient process.
So let's zoom out for a second. We've just seen a really clever solution to a pretty tough problem. But what does it all mean for the bigger picture of chemistry?
This work is just a massive win for green chemistry. It's a completely new, metal-free way to make these molecules, and it starts with something as harmless as a vitamin. It all happens in one pot, which saves a ton of time and cuts down on waste. Plus, it works with incredible precision, building the molecule in the exact 3D shape they wanted. At the end of the day, this isn't just one new reaction, it's a powerful, sustainable new tool in the chemist's toolkit.
And this whole thing leaves us with a really fascinating thought, right? If something like vitamin B1 can be repurposed to perform such complex, modern chemistry, it really makes you wonder what other secrets are just hiding in plain sight in nature. What other common, natural molecules are just waiting for us to discover them as the catalysts for the next generation of chemical synthesis?